Hello there, and welcome to Physics with William, where we explore the mysteries of the universe in a way that is as easy to follow as it is intriguing. Tonight, we dive into a subject that plays a critical role in our lives yet often escapes our understanding: radiation. It's one of those things that surrounds us every day, from the light we see to the heat we feel. But how many of us really know what it's made of or how it works at the deepest level? Radiation, it seems so simple on the surface, but the deeper we look, the more complex it becomes. Just like the invisible air we breathe, radiation is ever present and part of everything around us. Think about light, for instance. It comes to us from the sun, from light bulbs, and even from screens. But light isn't just one thing. It's a whole range of electromagnetic radiation that, despite being invisible to our eyes in its full spectrum, affects us in ways we often take for granted. What makes radiation so fascinating is that it can take many forms, and it's all composed of particles and waves that interact with the world in strange yet predictable ways. Radiation is, in essence, energy travelling through space. But how does it get there? What exactly is it made of? How do these tiny particles, often imperceptible to our senses, have such a profound impact on the world we live in? Let's uncover some of these answers, but first I want to ask you something. Where are you listening from right now? What time is it in your corner of the world? Funny, isn't it? How time and place can shape our experience, just as radiation shapes our surroundings in ways we can't always see. In this exploration of radiation, we'll look at how this invisible force plays a role not just in our daily lives, but in the very structure of the universe itself. If you find this journey intriguing, and if you think you'll enjoy the rest of the ride, feel free to give this video a like or subscribe. It helps bring this conversation to others who might enjoy it too. Now, let's set the stage for the story we're about to tell, as we explore the nature of radiation in quantum physics and uncover the mysteries of what it's really made of. Radiation is a concept we encounter in various forms every day, whether it's the warmth of the sun, the signals from our cell phones, or even the invisible X-rays used in medicine. But when we hear the word radiation, most people think of something dangerous, and while it's true that certain types of radiation can be harmful, not all radiation is bad. In fact, it's an essential part of the universe, fundamental to the way everything works. At its core, radiation is simply energy that travels through space. It can take the form of electromagnetic waves, particles, or both. This energy is emitted from various sources, like the sun, light bulbs, or even radioactive materials, and it travels across space until it interacts with something, whether it's a material, another particle, or even our own bodies. When you turn on a light bulb, the filament inside heats up and begins to emit radiation in the form of light. Similarly, when you place something in the microwave, radiation in the form of microwaves agitates the molecules in your food, making it heat up. These are examples of electromagnetic radiation, where energy is carried by waves travelling through space. These waves don't need a medium to propagate, meaning they can travel through the vacuum of space itself. This is why the light from the sun can reach us despite the empty void between us and it. Now, radiation can also exist as particles, and these are a bit trickier to understand. In the world of quantum physics, we deal with particles like photons, electrons, and alpha particles that can carry energy in ways that behave very differently from the waves we're familiar with. When we talk about radioactive decay, for instance, we're talking about a process where unstable atomic nuclei break down and release particles. These particles, such as alpha particles or beta particles, carry energy with them and move through the surrounding environment, interacting with whatever they encounter along the way. This type of radiation is called particle radiation. But what really sets radiation apart in the world of quantum physics is its dual nature. In quantum mechanics, radiation doesn't just act as a wave or a particle, but as both at the same time, depending on how we look at it. This is known as wave-particle duality, and it's one of the cornerstones of quantum theory. This idea can be difficult to wrap your head around because it doesn't fit neatly into the categories we're used to, but it's crucial to understanding how radiation behaves in the quantum world. This wave-particle duality means that radiation doesn't always act like something solid or predictable. Instead, it can behave in surprising ways depending on the circumstances. For example, light can travel as a continuous wave, but when we observe it, it can be thought of as discrete packets of energy, or photons. This helps explain why radiation behaves so differently at the quantum level, compared to how we experience it in our everyday lives. Now, you might be wondering how radiation interacts with matter. The answer lies in how energy is transferred through radiation. When radiation comes into contact with an object, it can either be absorbed, reflected, or transmitted, depending on the material. For example, when sunlight hits your skin, the energy is absorbed and converted into heat, which is why we feel warmer in the sun. In other cases, like when you're using a remote control, the infrared radiation from the device passes through the air and hits your television without being absorbed or converted into heat. It's the way that different types of radiation interact with different materials that gives us the many diverse effects we experience in our everyday lives. Radiation's role in the universe goes far beyond what we can directly sense. From the stars in the sky to the radioactive processes inside the Earth, radiation helps drive many of the fundamental processes of nature. It's the energy that powers the sun and allows it to shine. It's the force that heats up the Earth's core, contributing to the geological activity we experience. Even in space, radiation plays a key role in shaping galaxies, stars, and planets. The energy from distant stars and black holes is transported across vast distances through space, carrying information about the cosmos with it. In a very real sense, radiation is a constant and essential player in the story of the universe. It's more than just the heat we feel from the sun, or the energy in a microwave. It's the invisible force that keeps everything moving, from the tiniest particles to the largest celestial bodies. And as we dive deeper into the world of quantum physics, we'll start to see that radiation is not just a force we observe, it's a force that defines the way the universe itself behaves. As we continue on this journey, we'll explore how radiation fits into the quantum world and why it is so crucial to our understanding of the laws of nature. Radiation might seem like an abstract concept, something that only comes into play when we're dealing with very specific types of energy, but it's part of everything we experience. From light to heat to the particles that make up atoms, radiation is everywhere, and it's driving the fundamental processes that shape the universe. Let's now turn our attention to the fascinating relationship between radiation and quantum physics. The world of quantum particles is often described as one that exists beyond the realm of our senses. It's a place where things don't behave as we expect them to in our everyday lives, a world where particles exist in multiple states at once, and the boundaries between waves and particles blur. In this invisible realm, radiation behaves in strange ways, revealing a deeper complexity that challenges the way we think about energy, matter, and the very fabric of the universe. To understand radiation in quantum physics, we first need to get acquainted with this world of quantum particles. At its most basic, a quantum particle is any tiny, fundamental piece of matter or energy. These are the building blocks that make up everything in the universe, from the atoms in your body to the light that shines from a distant star. The particles we'll focus on here are the ones that make up radiation. One of the most well-known quantum particles is the photon, which is the particle of light and in many ways the carrier of radiation. But photons are just one type of quantum particle. There are many others, like electrons, protons, and neutrons, each playing a crucial role in the way energy behaves, including radiation. To understand how radiation works at this level, we have to look at the behavior of these particles. Quantum particles don't behave like macroscopic objects, which follow the predictable laws of classical physics. Instead, they behave in ways that seem almost counterintuitive. For example, a quantum particle like a photon doesn't have a definite position or momentum in the way we might expect a tennis ball or a car to. Instead, it exists in a state of probability, meaning that its exact location and speed are uncertain until we measure them. This idea is captured by the Heisenberg uncertainty principle, which tells us that there's a fundamental limit to how precisely we can know both the position and momentum of a quantum particle at the same time. This uncertainty isn't due to a lack of knowledge, it's a fundamental feature of the quantum world itself. What's even more surprising is that quantum particles can exist in multiple states simultaneously. Take the case of a photon. A photon can travel as a wave, spreading out across space and carrying energy, or it can be observed as a discrete particle. This duality of wave and particle nature is one of the key concepts of quantum mechanics, known as wave-particle duality. When a photon is not being measured, it behaves like a wave, spreading out over a range of possible positions, but when we observe it, it collapses into a single particle at a specific point. This idea challenges our classical understanding of particles, which are supposed to have definite properties, like position and velocity at all times. In the quantum world, particles like photons can behave both as waves and particles depending on how they are observed. It's as if the particle knows when it's being watched, and in response it behaves differently. This wave-particle duality is especially important when we talk about radiation. Radiation, in many forms, is made up of these quantum particles. Light itself is made up of photons, and the radiation we experience from things like radio waves, microwaves, or X-rays also involves photons, each carrying energy in a very specific way. This means that radiation doesn't just exist as a simple stream of energy moving through space. It exists as particles that interact with the world around them, much like billiard balls bouncing off each other, but at the same time they spread out like waves, influencing multiple points at once. This behavior of quantum particles gets even stranger when we consider how they interact with each other and with matter. In the quantum world, particles don't just interact through simple, direct collisions. Instead, they influence each other through fields, invisible forces that permeate all of space. For example, electromagnetic radiation, which includes visible light and other types of radiation, is carried by the electromagnetic field. This field is everywhere, even though we can't see it. When a photon travels through space, it moves through this electromagnetic field, and its energy is transferred through interactions with other particles in the field. But radiation doesn't just stay within the confines of the electromagnetic spectrum. It extends into the realm of particle radiation, where particles like electrons or neutrons are the key players. These particles are not merely carriers of radiation, but are themselves sources of radiation in certain circumstances. For instance, when an unstable atom decays, it releases radiation in the form of alpha or beta particles. These particles carry energy and can be absorbed by other atoms, transferring their energy in the process. This is how we get radiation from radioactive materials, particles that are emitted from unstable nuclei as they seek to become more stable. In the quantum world, particles like electrons don't follow simple, predictable paths. Instead, their behavior is governed by probabilities. Quantum mechanics uses wave functions to describe the likelihood of finding a particle in a particular location, or with a specific energy. The wave function doesn't tell us where the particle is exactly, but it gives us the probabilities of where the particle might be found. This probabilistic nature means that particles like electrons don't have well-defined positions or velocities until we observe them. They exist in a cloud of possibilities, and only when we measure them do they collapse into a single point. This concept is known as quantum superposition, where particles can exist in multiple states at once until observed. This probabilistic nature of quantum particles also means that radiation isn't as straightforward as we might think. When radiation interacts with matter, it doesn't always do so in a predictable way. The outcome of a radiation interaction can depend on a number of factors, like the energy of the radiation, the type of material it's interacting with, and the specific conditions under which the interaction occurs. For example, when radiation passes through a material, it might be absorbed, scattered, or transmitted depending on the material's properties, and the type of radiation. At the quantum level, these interactions are not always predictable, as they depend on the probability of various outcomes. The idea of quantum particles existing in multiple states at once and interacting through fields brings us to a broader understanding of the universe. Radiation isn't just something that travels through space, it's part of a dynamic and interconnected network of particles and fields that make up everything we experience. These quantum particles are constantly moving, interacting, and influencing each other, and their behaviours, while probabilistic, follow the rules of quantum mechanics in ways that give us insight into the fundamental workings of the universe. As we move forward in our exploration of radiation, we'll see how these quantum particles play a key role in understanding radiation's true nature. From the behaviour of photons to the emission of particles in radioactive decay, quantum particles are at the heart of radiation's existence. And while they may be invisible to our eyes, their influence is all around us, shaping everything from the technology we use to the fundamental forces of nature. Understanding the invisible world of quantum particles is the first step in understanding the very nature of radiation itself, and in the next part of our journey, we'll explore how radiation fits into the broader picture of quantum physics. When we look at light, it seems like such a simple and familiar thing. We see it every day, from the sunlight that brightens our world to the artificial light we use at night. Yet, despite its familiarity, light is one of the most perplexing phenomena in science. Is it a wave, or is it a particle? The answer, surprisingly, is both. Light exists in a dual form, as both a wave and a particle, and understanding this duality is key to understanding how radiation works in the quantum world. In the classical view, light was considered a wave. This idea, proposed by scientists like Thomas Young and Augustin Jean Fresnel in the 19th century, was based on experiments that showed light could interfere with itself just like waves do. When light passes through two closely spaced slits, it creates an interference pattern with alternating dark and light bands on the other side. This behaviour is characteristic of waves. When two waves meet, they can either cancel each other out or reinforce each other, depending on their phase. This discovery was a major breakthrough in understanding light, and it led to the wave theory of light being widely accepted. But as we delved deeper into the nature of light, something curious began to emerge. The wave theory didn't fully explain all the phenomena we observed with light. One of the most important puzzles came from the phenomenon of blackbody radiation, which is the radiation emitted by objects as they get heated. Classical physics predicted that the energy emitted by a heated object should increase infinitely as the temperature increases, a problem known as the ultraviolet catastrophe. This was clearly not the case, as objects like heated metal only emitted a specific range of radiation. This problem was solved in 1900 by Max Planck, who introduced the idea that energy is quantized. According to Planck, energy is not emitted in a continuous flow, but in discrete packets called quanta. This was a revolutionary idea, as it suggested that energy, including light, was made up of individual units rather than a continuous wave. Planck's work laid the foundation for what would later become quantum mechanics, and it hinted that light might not just be a wave but also a particle, a quantum particle. The true nature of light as both a wave and a particle was more clearly demonstrated in the early 20th century by Albert Einstein, who used Planck's idea of quantized energy to explain the photoelectric effect. The photoelectric effect occurs when light shines on a metal surface and causes electrons to be ejected from the metal. According to the wave theory, the energy of light should depend on the intensity of the light, and not on its frequency. But this wasn't what experiments showed. Instead, it was discovered that only light above a certain frequency could cause the photoelectric effect regardless of its intensity. Einstein proposed that light wasn't just a wave, but also a stream of particles called photons. Each photon carried a specific amount of energy, and this energy was directly related to the frequency of the light. Higher frequency light, like ultraviolet light, carried more energy than lower frequency light like red light. This explained why only light of a certain frequency could cause the photoelectric effect. Only photons with enough energy could knock electrons loose from the metal surface. Einstein's work earned him the Nobel Prize in 1921, and it solidified the idea that light has a dual nature. This wave-particle duality of light is one of the key principles of quantum mechanics. Light can behave like a wave, as it does in interference experiments, or like a particle, as it does in the photoelectric effect. But the most surprising aspect of light's dual nature is that it doesn't have to choose between being a wave or a particle. It can be both at the same time. This is a hallmark of quantum mechanics. Particles and waves are not distinct categories, but two different ways of describing the same phenomenon, depending on how we observe it. In the quantum world, light and other particles exist as wave functions, which describe the probability of finding a particle in a certain state, like a specific position or energy level. The wave function is not a physical wave, but a mathematical description of the possible states of the particle. When we measure the particle, the wave function collapses, and the particle takes on a definite position or energy. This is what gives light its wave-like behavior in some experiments and its particle-like behavior in others. This duality of light can be difficult to grasp because it goes against our everyday experiences. We don't see objects behaving like waves or particles in the same way light does. But in the quantum world, particles and waves are simply different aspects of the same reality. Light's ability to exist as both a wave and a particle is a reminder that the universe doesn't always behave the way we expect it to. It operates according to the strange and often counterintuitive rules of quantum mechanics. The wave-particle duality of light has far-reaching implications, not just for understanding radiation, but for the entire field of quantum physics. It shows us that the classical distinctions between waves and particles are not absolute, but are merely useful models to describe different aspects of the quantum world. And this duality is not limited to light. It applies to all quantum particles, from electrons to protons to even larger particles like atoms and molecules, under certain conditions. This understanding of light as both a wave and a particle also has practical applications. It helps explain the operation of devices like lasers, where light behaves as a coherent wave, and semiconductors, where light interacts with electrons in a more particle-like manner. It's the key to understanding many modern technologies, from fiber optic communications to the development of quantum computers, and it's all rooted in the strange and fascinating nature of light in the quantum world. As we continue our exploration of radiation in quantum physics, we'll see how this wave-particle duality shapes our understanding of energy, matter, and the very nature of reality itself. Radiation, in all its forms, is deeply tied to the quantum behavior of particles like photons, and the dual nature of light is just the beginning of the mysteries we will uncover as we dive deeper into the quantum realm. Electromagnetic waves are often referred to as the backbone of radiation, and for good reason. These waves are at the heart of most types of radiation, from the visible light we see every day to the X-rays that are used in medical imaging. In simple terms, electromagnetic waves are a form of energy that travels through space, carrying both electric and magnetic fields. These waves are capable of moving through the vacuum of space, which is a unique and important property that sets them apart from other types of waves that require a medium, like sound waves, to travel. The electromagnetic spectrum is the range of all types of electromagnetic radiation, and it spans a broad range of wavelengths and frequencies. At one end we have long wavelength, low-frequency radiation like radio waves, which are used for broadcasting and communication. At the other end, we have short wavelength, high-frequency radiation like gamma rays, which are produced by nuclear reactions. In between, there are a variety of other types of radiation, including microwaves, infrared radiation, visible light, and ultraviolet radiation. What makes electromagnetic waves so essential to our understanding of radiation is the fact that they carry energy in a way that allows them to interact with matter in significant ways. The energy carried by an electromagnetic wave is determined by its frequency. The higher the frequency, the more energy the wave carries. This is why ultraviolet light, for example, has more energy than visible light, and why gamma rays are so much more powerful than radio waves. To understand how electromagnetic waves work, it helps to first look at their structure. An electromagnetic wave consists of two perpendicular oscillating fields, one electric field and one magnetic field. These fields are in constant motion and are always perpendicular to each other, with the electric field oscillating in one direction and the magnetic field oscillating in a direction that's at a right angle to it. As the wave travels through space, both fields oscillate, transferring energy from one point to another. The electric field of an electromagnetic wave is created by charged particles like electrons, and it exerts forces on other charged particles. The magnetic field is created by moving charges, and it affects other moving charges. Together, the electric and magnetic fields interact with the world around them, enabling electromagnetic radiation to travel through space and interact with matter. This interplay between electric and magnetic fields is what gives electromagnetic waves their unique properties. One of the most important characteristics of electromagnetic waves is that they do not require a medium to propagate. Unlike sound waves, which need air or some other substance to travel through, electromagnetic waves can move through the vacuum of space. This is why we can receive sunlight from the sun or signals from distant satellites. The energy from the sun travels across the vast emptiness of space as electromagnetic radiation, reaching the Earth in the form of light and heat. Without the ability to travel through a vacuum, we wouldn't be able to experience sunlight or communicate via radio or television signals. Electromagnetic waves travel at the speed of light, which is approximately 299,792 kilometers per second in a vacuum. This is incredibly fast. So fast that light from the sun takes about 8 minutes and 20 seconds to reach us, despite the fact that the sun is about 150 million kilometers away. When electromagnetic waves interact with matter, they can be absorbed, reflected, or transmitted, depending on the material they encounter. For example, when visible light strikes an object, it may be absorbed by the object, causing it to heat up, or it may be reflected off the surface, allowing us to see the object. Similarly, radio waves can pass through walls, while X-rays can pass through the body, allowing us to create images of the inside of our body. The energy carried by electromagnetic waves is quantized, meaning that it is carried in discrete packets called photons. The energy of each photon is directly related to the frequency of the wave. High-frequency waves, like gamma rays, carry high-energy photons, while low-frequency waves, like radio waves, carry low-energy photons. This idea of quantized energy is a key aspect of quantum mechanics, and it's what allows us to understand how electromagnetic radiation interacts with matter on the atomic and subatomic levels. When electromagnetic waves interact with atoms and molecules, they can transfer energy to the electrons in those atoms. This can cause the electrons to move to a higher energy level, or it can knock electrons out of atoms altogether, as we see in the photoelectric effect. In some cases, the energy from the electromagnetic wave is absorbed by the material, causing it to heat up. In other cases, the wave may be reflected or transmitted, depending on the properties of the material. One of the most fascinating aspects of electromagnetic waves is their ability to carry information. Radio waves, for example, are used to transmit signals over long distances, carrying everything from music to television shows to internet data. Microwaves, which are a form of electromagnetic radiation, are used in radar systems to detect objects, and they are also used in microwave ovens to heat food. Each type of electromagnetic radiation has its own specific applications depending on its frequency and energy. The electromagnetic spectrum is organized according to the wavelength and frequency of the waves. At one end of the spectrum we have radio waves, which have the longest wavelengths and the lowest frequencies. These waves are used for communication, broadcasting and radar, Moving up the spectrum, we encounter microwaves, which are used for cooking, communication, and radar. Next, we have infrared radiation, which is used in thermal imaging and night vision. Visible light, the radiation we can see with our eyes, comes next, followed by ultraviolet radiation, which can cause sunburns and is used in sterilization. Further along the spectrum are X-rays and gamma rays, which have the shortest wavelengths and the highest frequencies, and are used in medical imaging and cancer treatment respectively. The fact that electromagnetic waves span such a wide range of frequencies means that they can interact with matter in different ways, depending on the energy they carry. Low-energy waves, like radio waves and microwaves, pass through many materials with little effect, while high-energy waves, like X-rays and gamma rays, can penetrate deep into materials and can even break apart atoms. This is why we use X-rays to look inside the human body or study the internal structure of materials in engineering. In summary, electromagnetic waves are a fundamental aspect of radiation and the backbone of much of the radiation we encounter in the world. They carry energy through space, and their behavior is shaped by the interplay of electric and magnetic fields, from the low-energy radio waves that carry signals to the high-energy gamma rays used in cancer treatment. Electromagnetic waves cover a vast range of frequencies, each with its own unique properties and applications. Understanding how these waves work is crucial to understanding radiation itself and the role it plays in the universe. As we continue our exploration, we'll see how electromagnetic radiation interacts with the quantum world, helping to shape the way matter behaves at the most fundamental level. The birth of quantum mechanics was a turning point in our understanding of the universe, and it fundamentally altered how we view the nature of radiation. Before the advent of quantum theory, the world of physics was governed by classical mechanics, which worked perfectly well for most everyday situations. Objects moved in predictable paths, forces acted in ways that could be measured and anticipated, and the behavior of light and other forms of radiation was understood within the framework of waves and particles. However, as scientists began to study the behavior of light and matter at the atomic and subatomic levels, they discovered that the classical theories could no longer explain the phenomena they were observing. The birth of quantum mechanics came about in the early 20th century, when physicists began to encounter a series of puzzles that couldn't be solved with classical physics. One of the earliest and most significant puzzles was the problem of black-body radiation. A black body is an idealized object that absorbs all the radiation that falls on it and emits radiation according to its temperature. Classical physics predicted that a black body would emit infinite amounts of energy at short wavelengths, known as the ultraviolet catastrophe, but experimental results showed that this wasn't the case. In fact, a black body emits a specific amount of radiation that peaks at a certain wavelength, and the intensity of the radiation drops off at higher frequencies. In 1900, Max Planck proposed a solution to this problem that marked the beginning of quantum theory. Planck suggested that energy is not emitted or absorbed in a continuous manner, as classical theory predicted, but in discrete packets, or quanta. These energy quanta, later known as photons, are the building blocks of radiation. Planck's idea was radical because it suggested that energy could be quantized, and that there was a fundamental limit to how much energy could be transferred at a time. This idea was a departure from the classical view that energy could be divided into infinitely small amounts. Planck's work was the first major step toward the development of quantum mechanics, and it laid the foundation for the way we understand radiation today. A few years later, in 1905, Albert Einstein built on Planck's work and made a groundbreaking contribution to our understanding of light and radiation. In his famous paper on the photoelectric effect, Einstein proposed that light itself is composed of particles called photons. He argued that when light strikes a material, it transfers energy to the electrons in the material, causing them to be ejected. The energy of the photons is directly related to the frequency of the light, and this explains why light of a certain frequency is needed to cause the photoelectric effect. Einstein's work on the photoelectric effect was instrumental in confirming the idea that radiation is made up of discrete particles, and it earned him the Nobel Prize in Physics in 1921. Einstein's ideas, along with Planck's, led to the development of the concept of wave-particle duality. This concept suggests that light and other forms of radiation can behave both as waves and as particles, depending on how they are observed. When light is behaving as a wave, it can interfere with other waves, just like water waves can create patterns of constructive and destructive interference. But when light is observed at a very small scale, it behaves like a particle with discrete energy levels. This dual nature of light and radiation is one of the fundamental principles of quantum mechanics. As scientists delved deeper into the nature of radiation, they found that the same principles apply to all forms of electromagnetic radiation, not just light. Radiation, in all its forms, is composed of discrete particles called photons, each carrying a specific amount of energy. The energy of a photon is directly related to the frequency of the radiation, with higher frequency radiation carrying more energy. This is true not just for visible light, but for all electromagnetic radiation, from radio waves to gamma rays. One of the key features of quantum mechanics is the idea of quantization, which means that certain properties, such as energy and angular momentum, can only take on specific, discrete values. This was a revolutionary concept because it challenged the classical view that these properties could vary continuously. In the quantum world, energy levels are restricted, and particles can only exist in specific states. This idea was central to the development of atomic theory, which explains the behavior of atoms and the emission and absorption of radiation by electrons. For example, when an electron in an atom absorbs a photon, it jumps to a higher energy level. But the electron cannot occupy just any energy level. It must jump to one of the specific quantized energy levels allowed by the atom. When the electron falls back to a lower energy level, it emits a photon of light with a specific energy. This process is known as the emission or absorption of radiation, and it is governed by the laws of quantum mechanics. The discrete energy levels of atoms are what give rise to the characteristic spectra of light, emitted by different elements. This explains why each element emits light of specific colors when it's heated or excited, and it is the basis for technologies like atomic clocks, lasers, and spectroscopy. The development of quantum mechanics also led to the realization that radiation is not just a product of interactions between matter and energy, but that it is fundamentally tied to the behavior of particles at the quantum level. Radiation in this sense is not just a phenomenon that happens in the world around us, it is an integral part of the quantum world itself, with particles and waves continuously interacting and transferring energy. This is the world of quantum fields, where radiation is both a manifestation of energy and a fundamental component of the universe's structure. One of the most important discoveries in the development of quantum mechanics was the concept of quantum fields. These fields are the foundation of all particles and forces in the universe, including radiation. In the quantum field theory, radiation is seen as a disturbance in these fields. For example, electromagnetic radiation is the result of fluctuations in the electromagnetic field, and it can be described as waves of energy traveling through space. Similarly, other forms of radiation, such as particle radiation, are disturbances in their respective fields. Quantum mechanics also introduced the idea that particles and waves are not distinct, separate entities, but that they are part of the same continuum. This means that radiation doesn't just exist as waves or particles, but as a combination of both, depending on the circumstances. The discovery of quantum mechanics and the understanding of radiation as a dual entity, both a wave and a particle, was a paradigm shift in our understanding of the universe. It allowed us to make sense of previously mysterious phenomena, like the behavior of light and the interaction of radiation with matter, in a way that classical physics could not. As quantum mechanics continued to evolve, scientists began to apply these principles to the study of radiation in more specific contexts, leading to breakthroughs in fields like nuclear physics, astrophysics, and condensed matter physics. In particular, the discovery of radioactivity in the late 19th century provided a real-world example of how quantum mechanics could explain radiation on a practical level. The radioactive decay of certain elements produces high-energy particles, such as alpha and beta particles, which are forms of radiation. The understanding of this process through quantum theory has led to advancements in fields ranging from medicine to energy production. The birth of quantum mechanics and its application to the study of radiation has had far-reaching consequences, not just for physics, but for technology and industry. Today, quantum mechanics underpins much of modern technology, including lasers, MRI machines, and even the computers we use to explore the quantum world. The principles of quantum mechanics continue to guide our understanding of radiation and energy, and they are central to the ongoing quest to understand the fundamental forces of the universe. As we continue to explore the mysteries of radiation, we will see how these quantum principles apply to the world around us, and how they shape the way we think about the universe. The birth of quantum mechanics not only transformed our understanding of radiation, but also opened the door to a new way of thinking about matter, energy, and the very nature of reality itself. The world of quantum physics is still full of mysteries, and radiation remains one of the most intriguing and important aspects of that world. As we move forward, we'll delve deeper into the nature of radiation and its connection to the quantum world, exploring how these fundamental particles and waves interact with matter and energy. Photons are the elementary particles of light, and they represent one of the most fundamental aspects of the universe. They are the carriers of electromagnetic radiation, and they play a crucial role in the way we understand light and radiation at the quantum level. To grasp the true nature of light, it's essential to understand what photons are, how they behave, and why they are so integral to the concept of radiation. At its core, a photon is a particle of light. But, as with many concepts in quantum physics, the term particle here is somewhat of a misnomer. In classical physics, a particle is something that has mass and occupies a specific location in space, like a tennis ball or a marble. However, photons are massless, and they don't have a fixed position in space until they are observed. Instead, they exist as quantum entities that can be described by wave functions, which provide the probabilities of where they might be found or how they might behave. Photons were first introduced as a concept by Albert Einstein in 1905, when he used them to explain the photoelectric effect. The photoelectric effect is a phenomenon in which light striking a material causes the ejection of electrons from the surface of that material. Classical wave theory of light had difficulty explaining this phenomenon, as it predicted that the energy of light should depend on its intensity, not its frequency. However, Einstein proposed that light was not just a continuous wave, but was made up of discrete packets of energy, which he called photons. The energy of each photon is proportional to the frequency of the light, and only photons with enough energy can knock electrons loose from a material. This work helps solidify the idea that light behaves both as a wave and as a particle, a concept known as wave-particle duality. What makes photons particularly interesting is that they are massless. Unlike particles such as electrons or protons, which have mass and experience gravitational pull, photons travel at the speed of light, approximately 299,792 kilometers per second in a vacuum, and they are unaffected by gravity in the same way. This property makes them unique among the fundamental particles, as they can carry energy and momentum without having mass. The fact that photons have no rest mass is why they can travel through the vacuum of space, from the sun to the earth, without needing a medium to propagate through. Despite their lack of mass, photons still carry energy, and the amount of energy they carry depends on their frequency. In the electromagnetic spectrum, photons with higher frequencies, such as gamma rays and X-rays, have more energy than photons with lower frequencies, like radio waves or visible light. The energy of a photon is directly proportional to its frequency, and it is inversely proportional to its wavelength. This means that the shorter the wavelength of the light, the higher the energy of the photon. This relationship is crucial for understanding the behavior of radiation, as it helps explain why different types of electromagnetic radiation have different effects on matter. The behavior of photons is governed by the principles of quantum mechanics, which means that their properties cannot be described in the same way we describe classical particles. In the quantum world, photons exist as wave functions, which represent the probability of finding a photon in a particular state. The wave function is not a physical wave, but rather a mathematical representation of the photon's possible locations or energies. When we measure a photon, its wave function collapses, and we observe a definite value, such as its position or energy. Until that moment of measurement, the photon exists in a superposition of all possible states, and we can only predict the probability of where it might be or what it might do. One of the most fascinating aspects of photons is their ability to interact with matter in ways that reveal the strange nature of the quantum world. For example, when photons interact with atoms, they can cause electrons in the atoms to move to higher energy levels. This is what happens in the process of absorption. When an atom absorbs a photon, the energy of the photon is transferred to the atom, exciting one of its electrons to a higher energy state. The electron can then fall back to a lower energy level, releasing a photon in the process. This is how light is emitted from atoms, and it is the basis for phenomena like fluorescence and phosphorescence. Photons also play a key role in processes like emission and absorption spectra. When atoms or molecules are excited by energy, such as heat or light, they can emit photons of specific wavelengths. The exact wavelengths of the emitted photons depend on the energy levels of the atom or molecule involved. This is why every element has its own characteristic emission spectrum, which can be used to identify the element. Similarly, when light passes through a material, certain wavelengths may be absorbed by the material, and the resulting absorption spectrum can provide information about the properties of the material. In addition to their interaction with atoms, photons can also interact with each other, although this interaction is extremely weak. This is a consequence of the fact that photons are massless and do not carry electric charge, so they do not interact with each other in the same way charged particles do. However, in certain circumstances, such as in the presence of strong electromagnetic fields or at very high energies, photons can interact through a process known as photon-photon scattering. This phenomenon, while rare, is an important aspect of the behavior of light in the quantum world. Photons are also responsible for the transmission of information across vast distances, which is why they are so essential to technologies like telecommunications and fiber optic networks. In these systems, photons carry information in the form of light signals, which travel through optical fibers at the speed of light. The ability of photons to transmit information over long distances with minimal loss makes them an ideal candidate for communication technologies. In the context of radiation, photons are the fundamental particles that carry energy across the electromagnetic spectrum. From the low-energy radio waves that carry signals to the high-energy gamma rays that are produced in nuclear reactions, photons are responsible for transporting energy through space. Understanding photons and their properties is essential for understanding radiation, as they are the particles that mediate the transfer of energy in most forms of radiation. Photons also play a key role in the development of many modern technologies. Lasers, for example, work by stimulating atoms or molecules to emit photons in a coherent manner, producing a highly focused beam of light. Similarly, in solar cells, photons from sunlight are absorbed by semiconductors, generating electricity through the photoelectric effect. These technologies rely on our understanding of photons and their ability to transfer energy and interact with matter in specific ways. In summary, photons are the elementary particles of light, and they are at the heart of radiation in the quantum world. Despite being massless, they carry energy and momentum, and they interact with matter in ways that are governed by the principles of quantum mechanics. Photons can behave both as particles and as waves, depending on how they are observed, and they are responsible for many of the phenomena we associate with light and radiation. From their role in the photoelectric effect to their ability to transmit information over long distances, photons are essential to our understanding of radiation and its impact on the world around us. As we continue to explore the nature of radiation in quantum physics, we'll see how photons help bridge the gap between the quantum and classical worlds, revealing the underlying principles that govern the behavior of light and energy. Energy and frequency are fundamental concepts that are intimately tied to radiation's behavior. They are the very core of what gives radiation its power, determining not just how radiation interacts with matter, but also how it propagates through space and influences the world around us. These two concepts are essential to understanding radiation in the context of quantum mechanics, and they form the foundation for much of the science behind electromagnetic radiation. At its most basic, the energy of radiation is directly related to its frequency. In the realm of electromagnetic radiation, frequency refers to the number of oscillations or waves that pass a given point in space per second. This is typically measured in hertz, where 1 hertz represents 1 oscillation per second. The frequency of a wave determines its energy, and this relationship is particularly important when we're dealing with radiation in its various forms, from radio waves to gamma rays. The connection between energy and frequency was first established in the early 20th century by Max Planck, whose work on blackbody radiation led him to the realization that energy is not emitted in a continuous flow, but in discrete packets, which he called quanta. This concept of quantization was a pivotal breakthrough in the development of quantum mechanics, and it laid the groundwork for our understanding of radiation's energy. Planck's equation, which relates the energy of a quantum of radiation to its frequency, is simple yet profound. The energy of a photon, which is the elementary particle of light, is equal to Planck's constant multiplied by the frequency of the radiation. This is written as energy equals Planck's constant multiplied by frequency. This relationship, now known as Planck's law, tells us that the higher the frequency of radiation, the more energy each photon carries. High-frequency radiation, such as gamma rays, carries more energy per photon than low-frequency radiation, such as radio waves. This is why radiation with higher frequencies can be more dangerous or more effective in certain contexts, because it has more energy to transfer. For example, gamma rays and X-rays can penetrate the human body and cause damage to cells because their photons carry much more energy than visible light or radio waves. This direct link between energy and frequency is crucial when we think about the behavior of radiation in the quantum world. When radiation interacts with matter, it is the energy of the radiation that plays the primary role in determining the outcome of that interaction. For instance, when a photon with sufficient energy collides with an electron, it can cause the electron to be ejected from its atom, a phenomenon known as the photoelectric effect. If the photon does not have enough energy, that is, if its frequency is too low, it won't be able to cause the electron to be ejected. This threshold frequency is specific to the material and depends on the binding energy of the electron in the atom. Energy and frequency are also central to understanding the electromagnetic spectrum. The electromagnetic spectrum encompasses all types of electromagnetic radiation, from the low-energy, long-wavelength radio waves to the high-energy, short-wavelength gamma rays. Each type of radiation in the spectrum has its own characteristic frequency and wavelength, which in turn determines its energy. The entire spectrum is continuous, meaning that it includes all possible frequencies, from the very low to the very high. However, the energy of radiation varies greatly depending on its position in the spectrum. Radio waves, for example, have the longest wavelengths and the lowest frequencies, and therefore the lowest energies. They are used for communication from AM/FM radio to cell phone signals, and they interact with matter in a relatively gentle way. Microwaves, which are just a step up in frequency from radio waves, have more energy and can be used to heat food in microwave ovens by exciting the water molecules in the food. As we move further up the spectrum, the frequency increases and so does the energy of the radiation. Infrared radiation, which is experienced as heat, has a higher frequency and energy than microwaves, while visible light has even higher frequencies and energies. At the high end of the spectrum, ultraviolet light, X-rays and gamma rays have much shorter wavelengths and much higher frequencies, meaning they carry significantly more energy. Ultraviolet radiation is known for its ability to cause sunburns, as its higher energy can damage skin cells. X-rays and gamma rays with even higher frequencies can penetrate deep into matter and are used in medical imaging and cancer treatment respectively. However, these higher energy radiations can also be harmful, as their photons can damage living tissue and DNA, potentially leading to cancer and other health problems. The energy of radiation also explains some of the phenomena that we observe with light and other types of radiation. For example, the colours we see in the visible light spectrum correspond to specific frequencies and energies of light. Red light has the lowest frequency and energy of the visible spectrum, while violet light has the highest. When light interacts with atoms or molecules, the energy of the photons can excite electrons to higher energy levels, leading to the emission of light of specific frequencies. This is what gives rise to the colourful patterns we see when atoms or molecules absorb and emit light at characteristic frequencies. In addition to its role in the electromagnetic spectrum, the concept of energy and frequency is also fundamental to the behaviour of radiation in quantum systems. In quantum mechanics, radiation is often described in terms of photons, each of which carries a discrete amount of energy. The energy of a photon is proportional to its frequency, as described by Planck's law. This means that when photons interact with matter, they transfer their energy in quantized amounts, leading to the discrete energy levels observed in atoms and molecules. This is why atoms can only absorb or emit light at specific frequencies. The energy of the photons must match the energy difference between the allowed energy levels of the atom. The relationship between energy and frequency is also key to understanding the behaviour of radiation in different contexts. For instance, in the case of radio waves, the energy of the photons is low enough that they can pass through the atmosphere without much interaction with matter. This is why radio waves are used for communication. They can travel long distances without being absorbed or scattered by the air. In contrast, high-frequency radiation like gamma rays carries so much energy that it can pass through solid materials, including the human body, and interact with the atomic nuclei inside. This is why gamma rays are used in medical imaging and cancer treatment, as they can penetrate deep into tissues, allowing for precise targeting of cells. The concept of energy and frequency also plays a critical role in technologies like lasers and solar cells. In a laser, atoms are stimulated to emit photons with very specific frequencies, leading to a coherent beam of light. In a solar cell, photons from sunlight are absorbed by semiconductor materials, transferring their energy to electrons and generating electricity. In both cases, the energy of the photons plays a direct role in the effectiveness of the technology. In conclusion, energy and frequency are the core of radiation's power. The energy of a photon is directly proportional to its frequency, and this relationship determines how radiation interacts with matter, how it propagates through space, and how it affects the world around us. Whether it's the low-energy radio waves that carry signals or the high-energy gamma rays used in medical treatment, the energy of radiation shapes its behaviour and its impact. Understanding the connection between energy and frequency is essential for understanding radiation in the quantum world, and it provides the key to unlocking many of the phenomena we observe in the universe. As we continue our exploration of radiation, we'll see how these principles apply to the behaviour of light, particles and energy in quantum systems, shaping the world of radiation at its most fundamental level. The The shift from classical physics to quantum mechanics was one of the most profound transformations in our understanding of the natural world. Before the dawn of quantum theory, classical physics, based largely on the works of Isaac Newton, James Clerk Maxwell and others, had successfully explained much of what we observe in the physical universe. Newton's laws of motion, for example, could accurately describe the behaviour of objects on a human scale, from the fall of an apple to the orbits of planets. Maxwell's equations, which describe electromagnetism, could explain how electric and magnetic fields interact and give rise to the behaviour of light. Classical physics provided a reliable framework for understanding everyday phenomena and mechanical systems. But as scientists began to probe deeper into the microscopic world, they encountered phenomena that classical physics could not explain. The study of radiation, especially the behaviour of light and heat at the atomic level, revealed fundamental inconsistencies between what classical theories predicted and what experiments observed. One of the most striking examples of this discrepancy was black-body radiation, which had long puzzled scientists. A black body is an idealized object that absorbs all incident radiation and emits radiation according to its temperature. Classical physics predicted that the intensity of radiation emitted by a black body would increase without bound as the frequency of the radiation increased, which was known as the ultraviolet catastrophe. In reality, however, experiments showed that the intensity of radiation from a black body peaked at a certain frequency and then dropped off, contrary to the predictions of classical physics. This failure of classical theory to explain blackbody radiation was one of the key problems that led to the birth of quantum mechanics. In 1900, Max Planck proposed a radical new idea that energy is not emitted or absorbed continuously, but in discrete packets, or quanta. This was a departure from the classical view, which held that energy could vary continuously. Planck's theory resolved the black-body radiation problem and laid the groundwork for the development of quantum theory. Planck's work was a major step forward, but it was Albert Einstein's explanation of the photoelectric effect in 1905 that brought the true nature of light into focus and cemented the idea that radiation is quantized. Einstein showed that light could not be understood purely as a wave, as classical physics suggested. Instead, light also behaved as a stream of particles, which he called photons. These particles carried energy in discrete quantities, and this explanation successfully accounted for the experimental observations of the photoelectric effect, where light striking a material caused the ejection of electrons. The energy of the ejected electrons depended on the frequency of the light, not its intensity, which could only be explained if light consisted of discrete packets of energy. The photoelectric effect was a key experiment that demonstrated the need for a new framework, quantum mechanics, because it showed that classical wave theory could not fully account for the behaviour of light. Einstein's insight into the particle nature of light was one of the first steps in the broader transition from classical to quantum thinking, and it highlighted the inadequacy of classical theories when applied to phenomena at the atomic and subatomic scales. Around the same time, other strange phenomena were being discovered that further challenged classical physics. For example, the atom itself could not be understood using classical mechanics. In classical physics, electrons orbiting the nucleus of an atom would continuously radiate energy and spiral inward, eventually collapsing into the nucleus. Yet, atoms are stable, and they do not collapse. This apparent contradiction led Niels Bohr to propose a new model of the atom in 1913, which incorporated Planck's and Einstein's ideas about quantized energy. Bohr's model suggested that electrons could only occupy certain discrete energy levels in an atom, and they could move between these levels by absorbing or emitting specific amounts of energy. This was the beginning of the understanding that atomic systems, like radiation, are governed by quantized rules that differ from the continuous nature of classical physics. The idea that energy, light, and matter could only exist in discrete quantities, or quanta, was a radical departure from classical thinking. In classical physics, Objects could have any energy, depending on their motion or position. But in quantum mechanics, only specific quantized energy levels were allowed, and the behavior of particles and waves was governed by probability rather than certainty. This shift in thought, from the determinism of classical mechanics to the probabilistic nature of quantum mechanics, had profound implications for how we understood the universe. Classical physics had provided a clear, predictable view of the world, where objects and forces followed well-defined laws. But quantum mechanics introduced a new set of rules that described a world where particles could exist in multiple states at once, where they could be in more than one place at the same time, and where events were governed by probabilities rather than certainties. One of the most challenging and groundbreaking aspects of quantum mechanics was the introduction of wave-particle duality. This concept suggested that particles, such as electrons and photons, could exhibit both wave-like and particle-like behavior, depending on how they were observed. This was something entirely foreign to classical physics, where waves and particles were thought to be distinct and separate categories. In the quantum world, however, these two categories merged, and a single entity could behave like both a wave and a particle. This realization was one of the key shifts in thought that came with the advent of quantum mechanics. Perhaps the most famous example of wave-particle duality is the double-slit experiment, which was originally performed with light, but later repeated with electrons and other particles. In this experiment, light or particles are directed at a barrier with two slits, and the resulting pattern on a screen is observed. When light is sent through the slits, it behaves like a wave, creating an interference pattern on the screen, with alternating dark and light bands. However, when individual photons are sent one at a time, they still create the same interference pattern, suggesting that each photon behaves like both a particle and a wave, depending on how it is observed. This experiment and others like it demonstrated that the classical notions of particles and waves were inadequate for describing the behavior of quantum systems. Another key shift that quantum mechanics brought was the idea of uncertainty. In classical physics, we could, in principle, measure the position and momentum of a particle with absolute precision. But in quantum mechanics, Heisenberg's uncertainty principle showed that there is a fundamental limit to how precisely we can know both the position and momentum of a particle at the same time. This was a radical departure from classical physics, where determinism ruled and the behavior of particles could be predicted with complete certainty. In the quantum world, however, uncertainty and probability are central to the way particles behave. The transition from classical to quantum thinking wasn't just a shift in the way scientists understood radiation, it was a complete reimagining of the very nature of reality. The classical view of the universe as a predictable machine, governed by fixed laws, was replaced by a quantum view, where uncertainty, probability, and wave-particle duality shape the behavior of everything from light to matter. This shift in thought not only changed the way scientists approached the study of radiation, but it also led to groundbreaking technologies like semiconductors, lasers, and quantum computers, which rely on the strange principles of quantum mechanics. As we continue to explore the world of radiation and quantum physics, we will see how these shifts in thought have allowed us to unlock new realms of understanding. The path from classical to quantum was not an easy one, and it required challenging many long-held beliefs about how the universe works. But this shift has given us a far deeper and more nuanced understanding of radiation, energy, and matter, one that continues to evolve as new discoveries are made. The world of quantum mechanics, with its strange and often counterintuitive rules, is still being explored, but its impact on science and technology is undeniable. The shift from classical to quantum was not just a change in theory, it was a revolution in how we think about the very fabric of reality itself. Radiation emission is a fundamental process in physics, one that plays a key role in many natural phenomena and technologies. Whether it's the warmth we feel from the sun, the light emitted by a glowing light bulb, or the radiation released by radioactive materials, Radiation emission is the mechanism by which energy is transferred through space in the form of electromagnetic waves or particles. To understand how radiation emission happens, we need to look at the underlying principles of energy release at the atomic and subatomic levels, as well as the factors that govern the process. At the heart of radiation emission is the concept of energy transitions within atoms or molecules. These energy transitions occur when an atom or molecule absorbs energy, causing its electrons to move from one energy level to another. When the system then returns to a lower energy state, it releases that energy in the form of radiation. This process is the foundation of radiation emission, and it can occur in various forms depending on the type of radiation involved. One of the most common forms of radiation emission is the emission of light, which occurs when electrons in an atom or molecule are excited to a higher energy level and then fall back to a lower energy level, releasing energy in the process. This can happen in a variety of ways, but the most straightforward example is fluorescence, where a substance absorbs light of a certain wavelength and then re-emits it at a longer wavelength. The energy that is released during this process is typically in the form of electromagnetic radiation, often visible light, although it can also be in the form of ultraviolet or infrared radiation. The process of radiation emission can be described in terms of quantum mechanics. In an atom, electrons exist in specific energy levels, also known as orbitals. These orbitals correspond to different levels of energy, with electrons in higher orbitals having more energy than those in lower ones. When an atom absorbs energy, whether from heat, light, or other forms of energy, the electrons can be excited to a higher energy level. This is known as excitation. However, this excited state is not stable, and the atom will eventually return to its lower energy state, a process known as de-excitation. During this transition, the atom releases the energy it absorbed, and this energy is emitted as radiation. The energy of the emitted radiation depends on the difference in energy between the two energy levels involved in the transition. The greater the energy difference, the higher the frequency, and therefore the shorter the wavelength, of the emitted radiation. This is why different elements emit different colours of light when they are heated or electrically excited. Each element has its own characteristic set of energy levels, and the radiation emitted corresponds to the specific energy transitions of that element. This principle is used in spectroscopy, a technique that allows scientists to identify elements and molecules based on the characteristic patterns of radiation they emit. While the emission of light from atoms is one of the most familiar forms of radiation emission, radiation can also be emitted in the form of particles. This is particularly true in the case of radioactive decay, where unstable atomic nuclei release energy in the form of particles such as alpha particles, beta particles, or gamma rays. Radioactive materials like uranium or radon emit these particles spontaneously as part of their process of becoming more stable. In the case of alpha and beta decay, the emission of particles occurs when an unstable nucleus undergoes a transformation. In alpha decay, the nucleus ejects an alpha particle, which consists of 2 protons and 2 neutrons. This process reduces the mass and atomic number of the original nucleus, resulting in the formation of a new element. Beta decay involves the emission of beta particles, which are high-energy electrons or positrons, and occurs when a neutron in the nucleus decays into a proton. These types of radioactive decay are governed by the weak nuclear force, one of the fundamental forces in nature, and they release energy in the form of the emitted particles. Gamma radiation, on the other hand, is a form of electromagnetic radiation, like X-rays or visible light, but with much higher energy. It is emitted when an unstable nucleus undergoes a transition from a higher energy state to a lower energy state, without a change in the number of protons or neutrons. Gamma radiation is often associated with nuclear reactions and is emitted alongside other forms of radiation, such as alpha or beta particles, during the decay of radioactive materials. The process of radiation emission is governed by the laws of quantum mechanics, which describe how particles and energy behave on the smallest scales. Quantum mechanics tells us that energy levels in atoms are quantized, meaning they exist in discrete values rather than a continuous range. This is why radiation is emitted in specific amounts, or quanta, and why we observe distinct lines in atomic spectra. It also explains the wave-particle duality of radiation. While we often think of light as a wave, in reality, it also behaves like a particle, a photon, with a specific energy that corresponds to the frequency of the radiation. Another important concept related to radiation emission is the idea of spontaneous and stimulated emission. Spontaneous emission occurs when an excited atom or molecule releases energy on its own, without any external influence. This is the process that occurs naturally in fluorescence and radioactive decay. Stimulated emission, on the other hand, occurs when an atom or molecule is induced to release energy by the presence of an external photon. This process is the basis for the operation of lasers. In a laser, atoms or molecules are excited to higher energy levels, and then stimulated emission is used to produce a coherent beam of light, with all the photons having the same frequency and phase. The emission of radiation can also be influenced by temperature. When objects are heated, they emit radiation in the form of electromagnetic waves, with the intensity and wavelength of the emitted radiation depending on the temperature of the object. This is described by Planck's law, which gives the intensity of radiation emitted by a black body at different temperatures. As an object's temperature increases, it emits more radiation, and the peak wavelength of the radiation shifts to shorter wavelengths. This is why hot objects like the filament in a light bulb or the surface of the sun emit visible light, while cooler objects like the Earth emit infrared radiation. The process of radiation emission is also critical to our understanding of energy transfer in the universe. Radiation is one of the primary ways in which energy is transferred through space. In the case of the sun, for example, radiation emission is how energy generated in the sun's core reaches the Earth. The sun emits vast amounts of electromagnetic radiation, including visible light, ultraviolet light, and infrared radiation, which travel across the vacuum of space to warm the Earth and provide the energy necessary for life. Similarly, the heat we feel from a fire or a stove is the result of radiation emitted by the hot surfaces, transferring energy to our skin. In conclusion, radiation emission is a key process in the world of physics, and it occurs whenever an atom or molecule transitions from a higher to a lower energy state, releasing energy in the form of electromagnetic radiation or particles. Whether it's the emission of light from atoms, the radiation emitted by radioactive materials, or the energy radiated by hot objects, radiation emission is governed by the principles of quantum mechanics and plays a fundamental role in the transfer of energy through space. Understanding how radiation is emitted helps us better comprehend the behavior of matter and energy, both at the atomic level and in the broader universe. As we continue to explore the world of radiation, we will see how these principles apply to the technologies we use every day and how they shape the natural world around us. The behavior of atoms in relation to radiation is at the heart of many physical phenomena, from the light emitted by stars to the process of photosynthesis in plants. Atoms, as the basic building blocks of matter, are directly involved in both the emission and absorption of radiation. These processes not only explain how radiation interacts with matter on a microscopic scale, but also illuminate how energy moves through systems, whether it's in the form of light, heat, or other types of electromagnetic radiation. To understand the role of atoms in emitting and absorbing radiation, it is important to first consider the structure of an atom. An atom consists of a dense nucleus made of protons and neutrons, surrounded by a cloud of electrons. These electrons exist in discrete energy levels or orbitals around the nucleus, with each energy level corresponding to a specific amount of energy. The key to understanding how atoms interact with radiation lies in the way these electrons behave when they gain or lose energy. Absorption of radiation. Absorption occurs when an atom absorbs a photon of light, or other forms of radiation, and uses the energy of that photon to move an electron from a lower energy level to a higher one. This is called an electronic transition. In other words, when a photon collides with an atom, it can transfer its energy to an electron, causing that electron to be excited to a higher energy state. This only happens if the energy of the photon matches exactly the energy difference between two energy levels in the atom. If the photon's energy does not match this difference, no absorption occurs. The process of absorption depends on the frequency or energy of the radiation. Photons of higher energy, such as ultraviolet light or X-rays, are capable of exciting electrons to much higher energy levels, while lower energy photons, like those of infrared radiation, only excite electrons to a smaller extent or to lower energy levels. This is why different materials absorb different frequencies of light or radiation. The specific energy levels of the electrons in an atom or molecule determine which wavelengths of light can be absorbed. For example, when sunlight strikes the Earth's atmosphere, different wavelengths of light are absorbed by different molecules. The ozone layer absorbs most of the harmful ultraviolet radiation from the sun, while visible light passes through the atmosphere and reaches the surface, where it can be absorbed by plants and other objects. This selective absorption is a direct result of the way atoms in these materials are structured and how their electrons can absorb photons of certain energies. Emission of radiation. Once an atom has absorbed energy, it doesn't stay in the excited state forever. The excited electron is unstable and eventually returns to its lower energy state, releasing the excess energy in the form of radiation. This process is known as emission. The energy released during this transition is typically in the form of a photon, and the energy of the emitted photon corresponds to the difference in energy between the two states. There are two primary types of emission: spontaneous emission and stimulated emission. Spontaneous emission occurs when an excited atom naturally returns to a lower energy state without any external influence. The photon that is emitted has a specific energy, corresponding to the energy difference between the excited and lower states of the atom. This process is random in terms of when the atom will release the photon, but the energy of the photon is determined by the energy levels of the atom. Stimulated emission, on the other hand, occurs when an atom is stimulated by an external photon to return to a lower energy state. In this case, the external photon causes the atom to release a photon of identical energy, phase, and direction. This is the principle behind the operation of lasers. In a laser, atoms or molecules are excited to higher energy levels, and when they undergo stimulated emission, they emit photons that are coherent. That is, they have the same frequency and phase, and are all emitted in the same direction. The coherent nature of the photons makes the light from a laser very different from the light emitted by most other sources, where photons are emitted randomly in all directions. The process of emission can occur at various wavelengths, depending on the energy transition involved. For instance, when atoms in a gas like hydrogen absorb energy, they can emit radiation in specific wavelengths of light. This emission is responsible for the characteristic spectra of elements. Each element has its own unique set of energy levels, and when the atoms of that element emit light, they produce a spectral line pattern that is specific to that element. This phenomenon is used in spectroscopy, which allows scientists to identify the composition of distant stars and galaxies by analysing the light they emit. Energy levels and the quantization of radiation. At the heart of emission and absorption lies the concept of quantized energy levels. In classical physics, energy could be continuously varied, meaning that an electron could occupy any energy level. However, in quantum mechanics, energy levels are discrete. This means that an electron can only occupy certain allowed energy levels, and the energy it absorbs or emits must correspond to the difference between these levels. This quantization of energy leads to the emission and absorption spectra of atoms being made up of discrete lines rather than continuous bands. The reason for this quantization lies in the nature of the atom itself. Electrons in an atom exist in stable orbitals around the nucleus, and each orbital corresponds to a specific energy. When an electron absorbs energy and moves to a higher orbital, it is not simply gaining a bit of energy, it is making a quantum leap to a discrete quantized energy state. When it returns to a lower energy state, it releases an exact amount of energy in the form of a photon, which has a specific wavelength and frequency. The energy differences between these levels are what give rise to the specific wavelengths of light emitted or absorbed by different elements. For example, in the hydrogen atom, the energy difference between the first and second energy levels corresponds to ultraviolet light, while the difference between the second and third levels corresponds to visible light. These specific transitions are responsible for the characteristic emission and absorption spectra of elements. Applications of atomic emission and absorption. The processes of emission and absorption are not just theoretical concepts. They have many practical applications. One of the most common examples is in the field of spectroscopy, where the light emitted or absorbed by atoms is analysed to determine the composition of materials. For instance, astronomers use spectroscopy to study the light emitted by stars, galaxies, and other celestial objects. By examining the spectral lines of light, scientists can determine the elements present in distant stars and measure their physical properties, such as temperature and motion. Another application of atomic emission and absorption is in the development of technologies like lasers and fluorescent lights. Lasers, as mentioned earlier, rely on stimulated emission to produce coherent light, and they have countless applications in fields ranging from medicine to telecommunications. Fluorescent lights work by exciting atoms in a phosphor coating, causing them to emit visible light when they return to lower energy states. The ability to control the emission and absorption of radiation is fundamental to the design of many modern technologies. In medicine, the principle of radiation absorption and emission is applied in imaging techniques like X-rays and MRI. In X-ray imaging, high-energy photons pass through the body, and the varying absorption of these photons by different tissues creates an image of the internal structures. In MRI, the absorption and emission of radiofrequency radiation by hydrogen atoms in the body are used to create detailed images of organs and tissues. Conclusion: atoms play a central role in the emission and absorption of radiation. These processes, governed by the principles of quantum mechanics, are responsible for the light we see, the radiation we use in technology, and the interactions of matter at the atomic and molecular levels. The emission and absorption of radiation depend on the movement of electrons between discrete energy levels within atoms, and these energy transitions result in the release of photons with specific energies. Understanding how atoms emit and absorb radiation has not only deepened our understanding of the quantum world, but has also led to many important applications in science, medicine, and technology. From the light emitted by stars to the lasers in modern electronics, the ability to manipulate atomic transitions and control radiation is essential to our technological world. Quantum fields and radiation are deeply intertwined concepts in modern physics. In the classical view of the world, matter and radiation were treated as distinct entities, with matter being composed of solid objects and radiation being a form of energy travelling through space. However, in the quantum mechanical view, both matter and radiation are seen as manifestations of quantum fields, which are fundamental to the behaviour of all particles and forces in the universe. Understanding quantum fields is essential for grasping how radiation is emitted, absorbed, and interacts with matter. To begin, let's explore what a quantum field is. In quantum field theory, QFT, every fundamental particle, such as an electron, a photon, or a quark, corresponds to a quantum field that permeates all of space. These fields are not just abstract mathematical constructs, but are considered to be real entities that interact with one another. The particles we observe in the universe are simply excitations or disturbances in these fields, and these excitations carry energy and momentum. For example, an electron is an excitation of the electron field, while a photon is an excitation of the electromagnetic field. In this framework, radiation is viewed as a disturbance in a quantum field that propagates through space. When we think about electromagnetic radiation, we're talking about fluctuations in the electromagnetic field. These fluctuations create photons, which are the quanta, or smallest units, of the electromagnetic field, and these photons carry energy across space as electromagnetic radiation. The nature of the electromagnetic field itself, with its electric and magnetic components, is what gives rise to phenomena such as light, radio waves, X-rays, and other forms of electromagnetic radiation. Quantum fields are not limited to the electromagnetic field. There are quantum fields associated with every fundamental force and particle in the universe. For example, the gravitational field is described by quantum gravity, which is still a developing area of physics, and the Higgs field gives mass to particles through its interactions with them. However, the electromagnetic field and the radiation it produces are some of the most well-understood examples of quantum fields in action. One of the key ideas in quantum field theory is that particles and fields are intimately connected. In the classical world, we think of matter as consisting of discrete particles, and radiation as a separate form of energy that can interact with matter. But in the quantum world, particles and radiation are both seen as excitations of underlying fields. This leads to a more unified understanding of the universe, where both matter and radiation emerge from the same fundamental entities, quantum fields. This view of radiation is a departure from the classical wave theory of light, where radiation was considered to be a continuous wave travelling through space. In quantum field theory, radiation is understood to be quantized, meaning it is made up of discrete packets of energy called photons. Each photon corresponds to an excitation in the electromagnetic field, and the energy of a photon is proportional to the frequency of the electromagnetic wave. This is the basis for Planck's law, which relates the energy of a photon to its frequency, and it explains why higher frequency radiation, like X-rays and gamma rays, has more energy than lower frequency radiation, like radio waves and microwaves. The idea of quantum fields also helps explain phenomena such as the particle-wave duality of light. In quantum mechanics, light can be described as both a particle and a wave, depending on the context in which it is observed. This is because light, like all particles, is an excitation of a field, and its wave-like properties arise from the nature of the field itself. When light interacts with matter, it behaves like a particle, transferring energy in discrete amounts, photons. But when it propagates through space, it behaves like a wave, spreading out and interacting with other fields in a way that is characteristic of electromagnetic radiation. Quantum fields also provide the framework for understanding how radiation interacts with matter. When an electromagnetic wave interacts with an atom, the energy of the wave can be absorbed by the atom, exciting an electron to a higher energy level. This process is described by quantum electrodynamics, QED, the theory that describes the interaction between electromagnetic fields and charged particles. In QED, the interaction between an electron and a photon is mediated by the exchange of virtual particles, which are fluctuations in the electromagnetic field that allow the electron to absorb or emit radiation. This is why radiation can transfer energy to matter, causing atoms to absorb or emit light in specific wavelengths. One of the most profound implications of quantum fields is that they can explain the creation and destruction of particles. In classical physics, particles were thought to be stable objects that existed independently of their surroundings. But in quantum field theory, particles are seen as excitations of fields that can be created or destroyed when energy is added or removed from the field. This is why particles like electrons and photons can be created in high-energy environments, such as particle accelerators or in the intense heat of stars, and why particles can be destroyed when they interact with other particles or fields. An interesting example of this is the concept of virtual particles, which are short-lived particles that appear and disappear within quantum fields. Virtual particles are not directly observable, but they play a crucial role in mediating the interactions between real particles. For example, when two electrons interact, they exchange virtual photons, which mediate the electromagnetic force between them. These virtual particles allow for the transfer of energy and momentum between particles and are an essential part of understanding how radiation is emitted and absorbed in quantum systems. The relationship between quantum fields and radiation also has important implications for the concept of vacuum energy. In classical physics, the vacuum was thought to be empty space, devoid of any matter or energy. However, in quantum field theory, the vacuum is not truly empty. Instead, it is filled with fluctuating quantum fields that constantly generate and annihilate virtual particles. This quantum vacuum energy is thought to be responsible for phenomena like the Casimir effect, where two uncharged plates placed close together in a vacuum experience an attractive force due to the fluctuations of the electromagnetic field. The existence of vacuum energy has also been proposed as a possible explanation for dark energy, the mysterious force that is driving the accelerated expansion of the universe. In summary, quantum fields are the foundation of radiation in quantum mechanics. Radiation is not simply a form of energy traveling through space, but a disturbance in an underlying quantum field. Each type of radiation, from light to gamma rays, corresponds to an excitation of a specific quantum field, and the properties of that radiation depend on the characteristics of the field itself. The interaction between quantum fields and matter is what allows radiation to be emitted and absorbed, and it is through this interaction that energy is transferred from one place to another. The quantum field perspective provides a more unified understanding of the universe, where both matter and radiation emerge from the same fundamental principles. As we continue to explore the behavior of radiation in the quantum world, we will see how these fields govern the interactions of particles and radiation and shape the fundamental processes of the universe. The concept of energy quanta is central to understanding how radiation behaves, especially at the quantum level. Energy quanta are discrete packets of energy that are exchanged during interactions involving radiation, and they form the very foundation of quantum mechanics. In the classical view, energy was seen as a continuous flow, meaning that energy could be spread out evenly and measured in arbitrary amounts. However, in the quantum world, energy is quantized, meaning it is absorbed and emitted in specific discrete amounts called quanta. This idea radically changed our understanding of radiation and how it interacts with matter. The concept of quanta was first introduced by Max Planck in 1900 as part of his work on blackbody radiation. A blackbody is an idealized object that absorbs all radiation and emits energy based on its temperature. Classical physics, however, was unable to explain the observed pattern of radiation emitted by blackbodies, particularly at short wavelengths, the ultraviolet catastrophe. Planck proposed that energy could not be emitted or absorbed in continuous amounts, as classical physics suggested. Instead, he suggested that energy was emitted in discrete bundles, or quanta, and that the energy of each quantum was proportional to the frequency of the radiation. This was the first glimpse of the idea that energy is quantized, and it was a crucial step in the development of quantum theory. Planck's equation, which links energy and frequency, is expressed as energy equals Planck's constant multiplied by frequency. In this equation, Planck's constant is a very small number, and it represents the smallest possible unit of energy that can be exchanged in the form of radiation. The idea that radiation can only occur in discrete packets of energy, rather than as a continuous flow, was a profound departure from classical physics. This discovery laid the groundwork for the later development of quantum mechanics and helped to explain the behavior of radiation on the atomic and subatomic levels. Building on Planck's work, Albert Einstein extended the concept of energy quanta to explain the photoelectric effect in 1905. The photoelectric effect refers to the phenomenon where light shining on a metal surface causes electrons to be ejected from the metal. Classical wave theory predicted that the intensity of light, how bright it is, should determine whether electrons are ejected from the surface, with brighter light causing more electrons to be ejected. However, experiments showed that the ejection of electrons depended on the frequency of the light, not its intensity. For example, even dim light could cause electrons to be ejected if it had a high enough frequency, while bright light with a lower frequency would not cause electron emission at all. Einstein proposed that light was not just a wave, but was also composed of discrete packets of energy, photons. Each photon carried a specific amount of energy, and the energy of a photon was proportional to the frequency of the light. This meant that only light with a high enough frequency could provide the energy needed to eject electrons from the metal, which explained the observed results. Einstein's work on the photoelectric effect provided further evidence for the concept of energy quanta, and helped to establish the idea that light, and by extension, all radiation, was made up of discrete energy packets. The concept of energy quanta applies not only to light but to all forms of radiation, including radio waves, microwaves, X-rays and gamma rays. The energy of a quantum of radiation, or a photon, depends on the frequency of the radiation. Higher frequency radiation, such as X-rays or gamma rays, has more energy per photon than lower frequency radiation, such as radio waves or microwaves. This is why high-frequency radiation is more likely to cause damage to living tissue or other materials. It carries more energy and can have a greater impact on the atoms and molecules it interacts with. The quantization of energy also helps explain many other phenomena in the quantum world. For example, atoms and molecules can only absorb or emit radiation at specific energy levels. When an electron in an atom absorbs a photon, it can only be excited to a higher energy level if the energy of the photon exactly matches the energy difference between the two levels. This is why atoms and molecules have characteristic absorption and emission spectra. Each element has a unique set of energy levels, and when they absorb or emit photons, the energy of the photons corresponds to the difference between those levels. This phenomenon is used in many scientific techniques, such as spectroscopy, where the absorption or emission spectra of materials are analysed to identify the elements or compounds present. The concept of energy quanta also has important implications for the behaviour of radiation in other contexts. For instance, in black body radiation, the amount of radiation emitted by an object depends on its temperature. Planck's law, which relates the intensity of radiation emitted by a black body to its temperature, is based on the idea that radiation is emitted in discrete quanta. As the temperature of an object increases, it emits radiation at higher frequencies, and the total amount of energy emitted increases as well. This is why hot objects such as stars or heated metal emit light at higher frequencies, like visible light, and cooler objects, like the Earth, emit infrared radiation. One of the key insights provided by quantum mechanics is that radiation is not just a simple transfer of energy from one place to another. It involves complex interactions between particles and fields. In the quantum field theory, radiation is seen as a disturbance in a quantum field, and the quanta of radiation, photons, are excitations of this field. The interaction of photons with matter is governed by the principles of quantum electrodynamics, QED, the theory that describes how photons interact with electrons and other charged particles. In QED, the exchange of photons between particles is the mechanism by which electromagnetic forces are mediated. This interaction is described by the exchange of virtual photons, which are fluctuations in the electromagnetic field that allow particles to interact without physically touching. The concept of energy quanta is also essential to understanding modern technologies such as lasers, photovoltaic cells, and semiconductor devices. In a laser, photons are emitted in a highly controlled manner, with all the photons having the same energy and phase, creating a coherent beam of light. This is achieved by stimulating atoms or molecules to emit photons in a synchronized manner, and the energy of each photon corresponds to a specific transition between energy levels. Similarly, in solar cells, photons from sunlight are absorbed by semiconductor materials exciting electrons and generating electrical current. In both cases, the behavior of photons and their energy levels plays a critical role in the functionality of the device. The concept of energy quanta also underpins many of the phenomena that arise in nuclear physics. For example, the decay of radioactive elements involves the emission of energy in the form of particles or electromagnetic radiation, and this emission is quantized. In nuclear reactions, energy is released in discrete quanta, and this quantization is key to understanding how radiation is produced in nuclear processes such as fission and fusion. In conclusion, the concept of energy quanta is foundational to our understanding of radiation and its behavior. Energy is no longer seen as a continuous flow, but as discrete packets or quanta that are exchanged between particles and fields. This quantization explains a wide range of phenomena, from the behavior of light and the spectrum of atomic radiation to the interactions of particles in quantum field theory. The relationship between energy and frequency, and the way in which radiation is emitted and absorbed in quantized amounts, has profound implications for both our understanding of the physical world and the technologies we use in everyday life. As we continue to explore the quantum nature of radiation, we will see how the concept of energy quanta helps to explain everything from atomic transitions to the behavior of radiation in the universe itself. The uncertainty principle, introduced by Werner Heisenberg in 1927, is one of the most foundational and profound concepts in quantum mechanics. It challenges our classical notions of measurement, determinism, and the ability to observe the universe with perfect accuracy. The principle states that there are fundamental limits to how precisely we can know certain pairs of properties of a particle, such as its position and momentum, at the same time. This concept is essential for understanding radiation at the quantum level, because it fundamentally shapes how radiation behaves and interacts with matter. Heisenberg's uncertainty principle. At its core, the uncertainty principle is about the relationship between two observable properties of a particle, often referred to as conjugate variables. The most commonly discussed pair of conjugate variables is position and momentum, but there are other pairs, such as energy and time, that are also subject to uncertainty. The principle can be mathematically expressed as delta x times delta p greater than or equal to h over 4 pi. In this equation, delta x is the uncertainty in position, delta p is the uncertainty in momentum. H is Planck's constant, a fundamental physical constant in quantum mechanics. This inequality tells us that as we try to measure the position of a particle more accurately, reducing the uncertainty in x, the uncertainty in its momentum p increases. Conversely, if we measure the momentum more precisely, the uncertainty in the particle's position increases. The product of these uncertainties is always greater than or equal to a fixed value, meaning that both properties cannot be precisely known at the same time. Implications for radiation. While the uncertainty principle primarily applies to particles, its effects also extend to the behavior of radiation. Radiation, particularly electromagnetic radiation, is closely related to the behavior of quantum particles like photons, which are quanta of the electromagnetic field. When we try to measure radiation at the quantum level, the uncertainty principle imposes limits on how precisely we can know certain properties of the radiation. For example, consider the process of measuring the energy of a photon. According to the uncertainty principle, if we measure the energy of a photon with very high precision, there will be an associated uncertainty in the time over which the measurement takes place. The more accurately we try to measure the energy of the photon, the less precisely we can know the exact time of the measurement. This relationship between energy and time is captured in the energy-time uncertainty principle, which can be written as delta E times delta t greater than or equal to h over 4 pi, where delta E is the uncertainty in energy. Delta t is the uncertainty in time. This version of the uncertainty principle tells us that if the energy of a photon is measured very precisely, the duration of the interaction or measurement process must be uncertain. This principle explains why certain phenomena in quantum mechanics, such as the spontaneous emission of radiation, occur on very short timescales and cannot be precisely pinned down. The impact of uncertainty on radiation: emission and absorption. The uncertainty principle has direct consequences for the emission and absorption of radiation in quantum systems. When atoms or molecules emit or absorb radiation, they do so by transitioning between discrete energy levels. These transitions occur over very short timescales, and the uncertainty principle places limits on how precisely we can measure these transitions. For example, consider an atom that is transitioning from a higher energy level to a lower energy level, emitting a photon in the process. The uncertainty principle tells us that if the energy of the photon is measured very precisely, the time over which the transition occurs becomes uncertain. This means that the more accurately we try to measure the energy of the emitted photon, the less precisely we can determine when the emission took place. In fact, this uncertainty is closely related to the concept of natural line width, which refers to the spread of frequencies or energies that a photon can have when emitted by an atom. No photon has a single, perfectly defined energy, and the uncertainty principle provides a fundamental reason for this. The energy of the photon emitted during the transition between energy levels is not a single sharp value, but rather a range of values, with a width determined by the uncertainty in the time of emission. This broadening of the spectral lines due to the uncertainty in time is a direct manifestation of the uncertainty principle in the context of radiation. Quantum fluctuations and vacuum radiation. The uncertainty principle also leads to the phenomenon of quantum fluctuations, which are short-lived changes in the energy of a point in space due to the inherent uncertainty in the field's energy. These fluctuations are a consequence of the principle that even in a perfect vacuum, where no particles are present, there are still temporary fluctuations in the electromagnetic field. These fluctuations can give rise to the creation of virtual particles, pairs of particles and antiparticles that spontaneously appear and annihilate each other within a very short time, in accordance with the energy-time uncertainty. This idea of quantum fluctuations is also tied to the concept of vacuum radiation, or zero-point energy. The energy present in a vacuum, according to quantum field theory, is not truly zero, but instead fluctuates due to the uncertainty in the energy of the electromagnetic field. These fluctuations give rise to what is known as the Casimir effect, a physical phenomenon where two uncharged conducting plates placed in a vacuum experience a small attractive force due to these quantum fluctuations in the electromagnetic field. These vacuum fluctuations, although incredibly small, are a direct consequence of the uncertainty principle and show that radiation can exist even in a vacuum. They also demonstrate that the quantum world is inherently uncertain, with particles and fields constantly fluctuating in and out of existence on incredibly short timescales. The role of the uncertainty principle in particle physics. The uncertainty principle plays a significant role in particle physics, especially in the interactions between radiation and matter. When high-energy particles, such as those produced in particle accelerators, interact with other particles or fields, the uncertainty principle limits how precisely we can predict the outcome of these interactions. For example, when a high-energy photon interacts with an electron, the interaction is governed by the exchange of virtual particles. The energy and position of these virtual particles cannot be precisely known at the same time, and this uncertainty leads to a range of possible outcomes for the interaction. The uncertainty in energy and time also affects the lifetime of unstable particles, which decay into other particles over short timescales. The short-lived nature of these particles and the uncertainty in their energy are fundamental aspects of the behavior of radiation in particle physics. Heisenberg's uncertainty principle and the nature of reality. The uncertainty principle has deep philosophical implications for our understanding of the universe. It tells us that there are limits to how much we can know about the properties of particles, radiation, and the interactions between them. At the quantum level, certainty gives way to probability, and the universe is not a deterministic machine, but a realm of uncertainty and fluctuation. In the context of radiation, the uncertainty principle highlights the fact that radiation is not simply a continuous, predictable flow of energy. Instead, radiation is inherently probabilistic and governed by quantum rules. The emission and absorption of radiation, the interactions between photons and matter, and even the vacuum itself are all subject to uncertainty, and this uncertainty is an intrinsic part of the quantum world. Conclusion. The uncertainty principle is a cornerstone of quantum mechanics, and it profoundly impacts our understanding of radiation. It imposes limits on how precisely we can measure certain properties, such as the energy and time of radiation events, and it explains the probabilistic nature of radiation's interaction with matter. The principle is responsible for phenomena like the broadening of spectral lines and the fluctuations in the electromagnetic field, which give rise to virtual particles and vacuum radiation. As we continue to explore the quantum nature of radiation, we see that the uncertainty principle not only governs the behavior of radiation, but also shapes the way we understand the fundamental interactions of the universe. The quantum world is inherently uncertain, and this uncertainty is a defining feature of radiation, matter, and the very fabric of reality itself. Radiation's interaction with matter is a fundamental aspect of how energy is transferred and how the universe functions on both the macroscopic and microscopic scales. Whether we're talking about the light from a distant star reaching Earth, the way microwaves heat our food, or the ionizing radiation produced by radioactive materials, understanding how radiation interacts with matter is essential for explaining the behavior of radiation across different contexts. These interactions play a crucial role in fields ranging from medical imaging to materials science and nuclear physics. Radiation, at its core, is energy in the form of waves or particles that travels through space. The interaction of this radiation with matter depends on several factors, including the type of radiation, the energy of the radiation, and the properties of the material that the radiation encounters. These interactions can result in a range of effects, from simple absorption and reflection to more complex processes like ionization, excitation, or nuclear reactions. The basics of radiation. Interaction. When radiation interacts with matter, it can be absorbed, reflected, transmitted, or scattered. The outcome of these interactions depends on the nature of both the radiation and the material. The material's properties, such as its atomic structure, density, and composition, play a crucial role in determining how radiation behaves when it encounters the material. Absorption occurs when the energy of the radiation is taken up by the material. This is the process behind phenomena, like the heating effect we observe when radiation is absorbed by an object, such as a metal surface or the Earth absorbing sunlight. Reflection happens when radiation bounces off a surface without being absorbed. The angle and intensity of the reflected radiation depend on the surface properties and the angle of incidence. Transmission involves the radiation passing through a material. Whether radiation can pass through a material depends on the material's properties and the energy of the radiation. For instance, visible light can pass through glass, but ultraviolet light is absorbed by it. Scattering happens when radiation is deflected by particles or atoms in the material. The extent and direction of scattering depend on the interaction between the radiation and the atoms in the material. These basic types of interactions form the foundation for more complex processes, which are particularly relevant when we deal with high-energy radiation, such as X-rays or gamma rays, or interactions with materials at the atomic or nuclear level. Absorption and ionization. One of the most significant interactions between radiation and matter is absorption, particularly when it leads to ionization. Ionization occurs when an atom or molecule gains or loses electrons, resulting in the creation of charged particles, ions. This process is central to the effects of radiation, especially ionizing radiation, which includes ultraviolet, X-ray and gamma-ray radiation. When ionizing radiation interacts with matter, it has enough energy to knock electrons out of atoms or molecules, leading to the formation of ions. Ionizing radiation, like X-rays or gamma rays, has high enough energy to ionize atoms in living tissues, and this can cause cellular damage or even mutations that may lead to cancer. The energy of the incoming photon is absorbed by the atom, which ejects an electron and leaves behind a positively charged ion. The amount of ionization that occurs depends on the energy of the radiation and the material it interacts with. For example, in a material like air, when X-rays or gamma rays pass through, they can ionize the air molecules, creating free electrons and ions. In living tissues, ionization can disrupt molecular structures, leading to DNA damage and potentially cancer. The rate of ionization is often referred to as the linear energy transfer, LET, which measures the amount of energy deposited in the material per unit of distance traveled by the radiation. High LET radiation, like alpha particles, causes more ionization over a short distance, whereas low LET radiation, like gamma rays, spreads its energy over a longer distance. Excitation. In addition to ionization, radiation can cause excitation in atoms or molecules. Excitation occurs when an atom absorbs energy and its electron is promoted to a higher energy level. However, unlike ionization, excitation does not involve the removal of an electron from the atom. Instead, the electron is temporarily raised to a higher orbit or energy level within the atom, and when it returns to its original state, it releases the absorbed energy as radiation. For instance, when ultraviolet light interacts with atoms, it can excite electrons to higher energy states. When the atom de-excites and returns to its ground state, it releases energy in the form of visible light, a process called fluorescence. Excitation is a reversible process, and the atom or molecule can re-emit radiation when it returns to a lower energy state. Excitation plays a significant role in the emission spectra of atoms and molecules. The specific wavelengths of light emitted when atoms or molecules are excited and then return to a lower energy state are characteristic of the elements involved. This is why scientists use absorption and emission spectra to identify elements in distant stars or analyze chemical compositions in a laboratory. Compton scattering. When high-energy photons, such as X-rays or gamma rays, interact with electrons in matter, they can undergo a process known as Compton scattering. In this process, a photon collides with an electron, transferring some of its energy to the electron and causing the electron to be ejected from the atom. The photon loses some of its energy and is scattered at a different angle. Compton scattering is significant for several reasons. It provides insight into the behavior of high-energy radiation. It is used in medical imaging techniques like X-ray and gamma-ray imaging, as it helps explain how X-ray photons interact with tissues and materials. It contributes to radiation attenuation, or the reduction of radiation intensity, as photons lose energy during scattering events. The energy lost by the photon in Compton scattering depends on the angle at which it is scattered, with larger scattering angles leading to greater energy transfer to the electron. This scattering process can also provide valuable information about the electron density of the material the photon is interacting with, which is why it plays a role in technologies like positron emission tomography, PET scans. Photoelectric effect. The photoelectric effect is another key interaction between radiation and matter. It occurs when a photon is absorbed by an atom and ejects an electron from the atom's outer shell. This process requires that the energy of the incoming photon be equal to or greater than the binding energy of the electron in the atom. The photoelectric effect is more likely to occur with lower energy photons, such as X-rays or ultraviolet light, and is the primary interaction in materials like metals. In the photoelectric effect, the energy of the incoming photon is transferred to the electron, which is then ejected from the atom. This ejected electron is known as a photoelectron. The energy of the photoelectron depends on the energy of the incoming photon and the binding energy of the electron in the atom. The photoelectric effect is essential to technologies such as solar panels, where photons from sunlight are absorbed by semiconductor materials, causing the ejection of electrons and generating electricity, nuclear reactions and radiation. In addition to the atomic interactions described above, radiation can also interact with the nuclei of atoms. This is particularly true for high-energy radiation, such as neutrons or gamma rays, which can cause nuclear reactions. One of the most well-known examples of nuclear reactions induced by radiation is nuclear fission, the process by which a heavy atomic nucleus, such as uranium, splits into smaller nuclei when struck by a neutron. This reaction releases a tremendous amount of energy and is the basis for nuclear power plants and atomic bombs. Gamma radiation can also induce nuclear reactions, such as gamma-induced fission, or the photonuclear effect, where gamma photons interact with atomic nuclei, causing them to emit particles like neutrons or protons. These reactions are important in fields like nuclear physics and astrophysics. Attenuation of radiation. When radiation passes through a material, it loses intensity due to various interactions. This process, known as attenuation, occurs as the radiation interacts with the atoms or molecules in the material, leading to absorption, scattering, or other effects. The attenuation of radiation depends on the type of radiation, the energy of the radiation, and the properties of the material. For example, X-rays can pass through soft tissues with little attenuation but are absorbed or scattered by denser materials like bone. This difference in attenuation allows X-ray imaging to create detailed images of the inside of the body, with bones appearing white and softer tissues appearing darker. Conclusion. Radiation's interaction with matter is a complex process influenced by a variety of factors, including the type of radiation, the energy of the radiation, and the properties of the material involved. These interactions can lead to absorption, scattering, excitation, ionization, and even nuclear reactions depending on the energy and nature of the radiation. Understanding how radiation interacts with matter is crucial for applications ranging from medical imaging to nuclear energy production, as well as for protecting against the harmful effects of ionizing radiation. By studying these interactions, we can better understand how radiation behaves in different environments and use this knowledge to develop technologies that improve our lives, from cancer treatments to communication systems. Radiation plays a fundamental and essential role in the universe. From the formation of stars to the dynamics of galaxies, radiation is a key player in the processes that shape the cosmos. Whether we're talking about the light emitted by stars, the radiation from the remnants of the Big Bang, or the cosmic microwave background that permeates space, radiation is not just a byproduct of physical processes. It is a driving force that influences the behavior of matter on the largest and smallest scales. Understanding the role of radiation in the universe provides insight into everything, from the origins of the cosmos to the future of its expansion. The birth of the universe and cosmic radiation was crucial in the very early moments of the universe's existence. According to the Big Bang theory, the universe began as an incredibly hot, dense state, roughly 13.8 billion years ago. In the first moments after the Big Bang, the universe was a hot, glowing mass of energy and radiation, dominated by high-energy photons. As the universe began to expand and cool, these photons started to interact with matter in a way that eventually led to the formation of atoms. One of the key milestones in the history of the universe was the era of recombination, which occurred about 380,000 years after the Big Bang. During this time, the universe cooled enough for electrons and protons to combine and form hydrogen atoms. This allowed photons to travel freely through space for the first time, as the dense plasma of charged particles that previously scattered the light began to dissipate. The release of these photons is what we now observe as the cosmic microwave background, CMB radiation. The CMB is a faint glow that fills the universe and provides a snapshot of the universe in its infancy, offering valuable information about the early conditions of the cosmos. The CMB is often referred to as the afterglow of the Big Bang. Its discovery in 1965 by Arno Penzias and Robert Wilson provided one of the key pieces of evidence for the Big Bang theory. The CMB is a crucial component in understanding the early universe, as it provides a detailed record of the universe's temperature, density, and other physical properties at the time of recombination. The study of the CMB continues to offer insights into the nature of dark matter, dark energy, and the overall structure of the universe, stellar radiation, and the life cycle of stars. Radiation from stars is one of the most important sources of energy in the universe. Stars, like our Sun, generate energy through the process of nuclear fusion, which occurs in their cores. During fusion, hydrogen nuclei, protons, combine to form helium, releasing vast amounts of energy in the form of electromagnetic radiation. This radiation is what powers the star and is emitted in various forms, including visible light, ultraviolet radiation, and X-rays. The energy produced in the core of a star takes thousands to millions of years to reach the surface and be radiated into space. The radiation emitted by stars is responsible for a variety of important phenomena. For example, the Sun's radiation is the primary source of energy for life on Earth. It drives weather patterns, ocean currents, and the water cycle, and it is the energy source for photosynthesis, which sustains most life forms on Earth. The spectrum of radiation emitted by stars also tells astronomers a great deal about the star's temperature, size, and composition. By analysing the light from distant stars, scientists can determine their age, chemical makeup, and even their distance from Earth. As stars evolve, their radiation changes. A star's mass determines its life cycle. In stars like our Sun, nuclear fusion eventually shifts to heavier elements, and the star expands into a red giant before shedding its outer layers and becoming a white dwarf. During this process, the radiation emitted by the star changes in both intensity and frequency, transitioning from visible light to infrared radiation as the star cools. More massive stars, on the other hand, go through more violent processes, such as supernova explosions, which release enormous amounts of energy in the form of radiation, including gamma rays. These explosions are some of the most energetic events in the universe and can outshine entire galaxies for brief periods. Radiation and the expansion of the universe. Radiation also plays a key role in the large-scale dynamics of the universe. One of the most significant discoveries in modern cosmology is that the universe is expanding, and the rate of this expansion is actually accelerating. This acceleration is attributed to a mysterious form of energy called dark energy, which is thought to make up about 68% of the total energy content of the universe. Radiation itself is a form of energy that interacts with the expanding universe in subtle ways. For example, as the universe expands, the wavelength of the cosmic microwave background radiation stretches, and this phenomenon, known as redshift, is evidence of the universe's expansion. The redshift of light from distant galaxies also provides key evidence for the accelerating expansion of the universe. By studying the way that light and radiation from distant galaxies are redshifted, astronomers can trace the history of the universe's expansion and gain insights into its future. In addition to the role that radiation plays in the expansion of the universe, it is also a key tool for studying cosmic structures. Astronomers use radiation from various sources, including galaxies, nebulae, and quasars, to study the formation and evolution of the universe. Radiation in the form of X-rays, gamma rays, radio waves, and visible light allows us to observe phenomena such as black holes, neutron stars, and the formation of galaxies. These observations provide crucial insights into the fundamental laws of physics, including the behavior of matter under extreme conditions, radiation, and black holes. Black holes are one of the most fascinating and extreme manifestations of radiation in the universe. These objects are formed when massive stars collapse under their own gravity, creating a region of space where the gravitational pull is so strong that not even light can escape. Despite their name, black holes are not completely black. They emit radiation through a process known as Hawking radiation, named after physicist Stephen Hawking. According to quantum theory, black holes can emit particles and radiation due to quantum fluctuations near the event horizon, the boundary beyond which nothing can escape. The study of radiation around black holes is crucial for understanding their properties. For example, when matter falls into a black hole, it forms an accretion disk, a swirling mass of gas and dust that heats up to extreme temperatures, emitting large amounts of radiation, particularly in the X-ray spectrum. This radiation provides valuable information about the black hole's size, mass, and spin, and is one of the primary ways scientists observe black holes. Additionally, the radiation from distant supermassive black holes, which are thought to reside at the centers of most galaxies, can be detected and analyzed to understand the growth and evolution of galaxies. The intense radiation emitted by these black holes is often referred to as active galactic nucleus, AGN radiation, and can be detected across vast distances, providing insights into the dynamics of galaxies and the role of black holes in shaping the universe. Radiation from cosmic events, supernovae, gamma-ray bursts, and cosmic rays. Radiation from explosive events in the universe, such as supernovae and gamma-ray bursts, GRBS, plays an important role in the life cycle of stars and the formation of elements. A supernova is an extremely energetic explosion that occurs at the end of a massive star's life. The explosion releases enormous amounts of radiation, including visible light, ultraviolet, and X-rays, and can briefly outshine an entire galaxy. Supernovae are responsible for the creation and dispersion of heavy elements, which are essential for the formation of planets, life, and galaxies. The study of supernovae radiation allows astronomers to understand the processes of stellar death, nucleosynthesis, the creation of new elements, and the expansion of the universe. Gamma-ray bursts, GRBS, are among the most powerful and energetic events in the universe, producing intense bursts of gamma radiation. GRBS are thought to occur during the collapse of massive stars into black holes, or when two neutron stars merge. The radiation emitted during a GRB can be detected from billions of light years away, providing astronomers with valuable data about the end stages of stellar evolution and the extreme conditions that lead to these explosive events. Cosmic rays, which are high-energy particles originating from distant sources such as supernova and active galactic nuclei, also contribute to the radiation environment of the universe. These particles, mostly protons, travel through space at nearly the speed of light, and when they interact with the matter, they can produce secondary radiation, including gamma rays and neutrinos. Cosmic rays are a source of radiation that impacts the Earth's atmosphere, leading to phenomena like the auroras and contributing to the background radiation that surrounds us. Conclusion: radiation as a cosmic force. Radiation is not just an incidental part of the universe, it is a driving force behind many of the processes that shape the cosmos. From the cosmic microwave background that provides a snapshot of the universe's infancy, to the radiation emitted by stars, black holes, and exploding supernovae, radiation plays a central role in the dynamics of galaxies, the formation of elements, and the evolution of the universe itself. Radiation also serves as a tool for astronomers to probe distant objects and cosmic phenomena, allowing us to learn about the universe's structure, history, and future. As we continue to study radiation in all its forms, from the most energetic gamma rays to the faintest background radiation, we are uncovering the mysteries of the universe and gaining a deeper understanding of the forces that govern everything, from the smallest particles to the largest cosmic structures. Radiation is, in essence, the language of the universe, conveying information about the universe's past, present, and future. Radiation, in its various forms, has become an indispensable part of modern technology. From the light that powers our smartphones to the advanced medical devices that save lives, radiation is at the core of numerous technological marvels. The ability to harness the power of radiation, both visible and invisible, has revolutionized industries, from healthcare to communication to energy production. Understanding how radiation works and its applications has allowed scientists and engineers to develop technologies that have transformed our world. Medical imaging and treatment. One of the most important applications of radiation is in the field of medical imaging and treatment. Techniques like X-ray imaging, CT scans, computer tomography, and MRI, magnetic resonance imaging, rely on different forms of radiation to visualize the inside of the human body, diagnose diseases, and guide treatment. X-ray imaging. X-rays are a form of high-energy electromagnetic radiation that can penetrate the body. When X-rays pass through a body, they are absorbed by tissues in different amounts depending on the tissue's density. Denser materials, such as bones, absorb more X-rays and appear white on the resulting image, while less dense tissues like muscles and organs appear darker. This contrast allows doctors to examine bones for fractures, detect infections, or identify tumours. X-ray technology is widely used in dentistry, emergency rooms, and for routine checks like mammograms to detect breast cancer. CT scans. A CT scan uses a series of X-ray images taken from different angles and then combines them into a detailed, cross-sectional image of the body. This technology provides much more detailed images of soft tissues and organs than standard X-rays, helping doctors diagnose conditions like cancer, internal injuries, or infections. MRI. While MRI does not use ionizing radiation like X-rays or CT scans, it involves strong magnetic fields and radio waves to create detailed images of the inside of the body. MRI is particularly useful for imaging soft tissues such as the brain, spinal cord, muscles, and organs, allowing for the detection of neurological diseases, joint issues, and cancer. MRI has no known harmful effects and is considered one of the safest imaging methods available. Beyond imaging, radiation is also used in radiotherapy to treat cancer. In this approach, high-energy radiation is directed at tumours to damage the DNA of cancer cells, causing them to die or stop dividing. By carefully targeting the radiation to the tumour, doctors can destroy cancerous tissue while minimizing damage to healthy surrounding tissue. This has become one of the most effective ways of treating various forms of cancer, such as prostate cancer, breast cancer, and brain tumours. Nuclear power and radiation. Nuclear power is another significant technological marvel powered by radiation. Nuclear reactors harness the energy released by radioactive materials, specifically the process of nuclear fission, to generate electricity. In nuclear fission, the nucleus of a heavy atom, such as uranium or plutonium, splits into smaller nuclei, releasing a substantial amount of energy in the form of heat. This heat is used to produce steam, which drives turbines that generate electricity. Nuclear power plants are able to produce large amounts of energy with relatively small amounts of fuel, and they emit very little air pollution compared to fossil fuel-based power plants. As concerns about climate change and the environmental impact of fossil fuels grow, nuclear power offers a potential solution for generating large-scale electricity with low greenhouse gas emissions. While nuclear power has its risks, such as the potential for accidents or the long-term management of nuclear waste, it remains a crucial part of the global energy mix and a major technological achievement. Lasers and their applications. Lasers, light amplification by stimulated emission of radiation, are one of the most versatile and widely used technologies powered by radiation. A laser produces a concentrated beam of light by stimulating atoms or molecules in a material to emit photons in a controlled manner. The key characteristic of laser light is its coherence. All the photons emitted have the same frequency, phase, and direction, making the beam highly focused and intense. lasers have a broad range of applications in science, medicine, industry, and consumer electronics. Some of the most impactful uses of lasers include laser surgery. In medical procedures, lasers are used to cut or vaporize tissue with precision, such as in eye surgeries like LASIK, laser-assisted in situ keratomileusis, to correct vision problems. Lasers are also used to treat kidney stones, remove tumours, and perform delicate operations with minimal damage to surrounding tissues. Communication. Lasers are at the heart of fibre optic communication systems, which have revolutionised telecommunications. Fibre optic cables transmit light signals over long distances at very high speeds, allowing for the rapid transfer of data across the globe. Lasers enable this high-speed communication by emitting light that travels through optical fibres, enabling everything from internet browsing to phone calls. Manufacturing. Lasers are used in cutting, welding, engraving, and 3D printing. Their precision and ability to focus energy on small areas make them ideal for tasks that require high levels of accuracy, such as semiconductor manufacturing and the production of intricate parts for aerospace, automotive, and electronics industries. Radiation in the field of space. Exploration. Radiation also plays a crucial role in space exploration. In fact, radiation is one of the primary challenges that space missions must contend with. Space is filled with various forms of radiation, including cosmic rays, high-energy particles from the Sun and beyond, solar radiation from the Sun, and radiation from other celestial bodies. Spacecraft, astronauts, and satellites are all exposed to this radiation, which can have damaging effects on electronic equipment and biological systems. Solar power. The Sun is the primary source of radiation that powers our solar system. Solar panels on spacecraft, satellites, and rovers convert sunlight into electricity, providing power for exploration missions. For example, NASA's Mars rovers, like Curiosity and Perseverance, are powered by solar panels that convert sunlight into electrical energy to operate their instruments, communication systems, and mobility components. Radiation shielding. Protecting astronauts from harmful radiation in space is a key challenge for long-duration missions, such as those to the Moon or Mars. Shielding materials are developed to block or reduce the impact of space radiation, and researchers are continually working on advanced materials that can better protect astronauts during missions. Astronomical observations. Radiation from space is used in instruments such as telescopes and detectors to study distant galaxies, stars, and other celestial objects. Telescopes that detect X-rays, gamma rays, and radio waves have provided unprecedented insights into the structure and evolution of the universe, revealing phenomena such as black holes, neutron stars, and the cosmic microwave background radiation. Radiation in consumer electronics. Radiation plays a role in many consumer electronics that are integral to daily life. From televisions to smartphones to microwave ovens, radiation is used to perform a variety of functions. Microwave ovens. These appliances use microwaves, a form of electromagnetic radiation, to heat food. Microwaves interact with water molecules in the food, causing them to vibrate and generate heat. This technology has become a ubiquitous part of modern kitchens because it allows for rapid and efficient cooking and reheating. Television and smartphone displays. Modern flat-screen televisions and smartphones rely on the use of light-emitting diodes, LEDs, or liquid crystal displays, LCDs, to produce bright, clear images. The screens of these devices emit visible light through the use of various forms of radiation, including ultraviolet and visible light. OLED, organic light-emitting diode technology, which powers many modern displays, utilizes a form of radiation to produce brighter, more efficient screens. Radiation-based sensors. Various consumer devices, such as smoke detectors, rely on radiation-based sensors to detect dangerous particles. In the case of smoke detectors, A small amount of radioactive material is used to detect the presence of smoke particles in the air, setting off an alarm when dangerous levels are reached. Conclusion: radiation, in its many forms, powers a vast array of technological marvels that have transformed human life and society. From medical imaging and treatment to the harnessing of nuclear power, from lasers enabling high-precision surgeries and manufacturing to space exploration technologies, radiation is at the heart of modern technological progress. Understanding and harnessing the power of radiation has allowed scientists, engineers, and innovators to develop groundbreaking technologies that benefit humanity, improve our quality of life, and expand our reach into the cosmos. As we continue to explore new frontiers in science and technology, the role of radiation will only grow more significant, and its applications will evolve in ways we can only begin to imagine. Whether it's through the use of radiation in energy production, healthcare, communications, or space exploration, the continued development of radiation-based technologies promises to shape the future in profound ways. Radiation has long been a central concept in physics, shaping our understanding of the universe from the smallest particles to the largest cosmic structures. Yet, despite its ubiquity and significance, radiation remains an area of intense study and ongoing mystery, especially when viewed through the lens of quantum physics. As we have explored, radiation is not just a simple transfer of energy through space, but a complex phenomenon intricately tied to the behavior of quantum fields, particles, and waves. It is both a tool for discovery and a powerful force in nature, with applications that span the realms of medicine, technology, and even the vast cosmos. Over the years, the study of radiation has progressed from classical theories, which described it in terms of waves and particles, to the quantum mechanical framework, which reveals its more nuanced and sometimes perplexing nature. The idea that radiation can be described as both a wave and a particle, depending on how it is observed, was one of the first glimpses into the strange world of quantum mechanics. The concept of energy quanta, introduced by Planck and later extended by Einstein, completely transformed our understanding of radiation, showing that energy is not a continuous flow, but a discrete exchange that occurs in packets. This realization paved the way for a deeper exploration of radiation's behavior on the atomic and subatomic levels. Yet even with all that we know, there is still much to uncover about the nature of radiation in the quantum world. The uncertainty principle, for example, tells us that there are inherent limits to how precisely we can measure certain properties of radiation, such as its energy and time. These uncertainties are not due to experimental flaws, but are built into the fabric of the quantum universe itself. The probabilistic nature of radiation makes it both a challenge and an opportunity for scientists seeking to unravel the mysteries of the universe. Radiation also plays a critical role in some of the most fundamental processes of the universe, from the birth of stars to the evolution of galaxies. Cosmic radiation, which has travelled across the universe for billions of years, provides us with a window into the earliest moments of the universe's existence. The cosmic microwave background radiation, a remnant of the Big Bang, holds crucial information about the conditions of the early universe, helping us piece together the puzzle of cosmic history. Yet, much remains uncertain about the nature of the universe's expansion, the true nature of dark energy, and the role that radiation plays in these cosmic phenomena. In the realm of quantum mechanics, radiation continues to challenge our understanding of reality. The fact that radiation can behave as both a wave and a particle, depending on the circumstances, suggests that the universe operates in ways that defy our classical intuitions. Quantum fields from which radiation emerges continue to be a subject of deep investigation, as scientists seek to understand how these fields interact and govern the fundamental forces of nature. As our understanding of quantum physics evolves, so too will our understanding of radiation's role in the universe. Moreover, as technology advances, New techniques and instruments are allowing us to explore radiation in ways that were once unimaginable. From the study of high-energy cosmic radiation to the development of radiation-based technologies in medicine, communication and energy, we are continually pushing the boundaries of what we know. The applications of radiation, whether in the form of lasers, nuclear power, or medical imaging, continue to change the way we live and interact with the world. Yet, with every new discovery, new questions arise. Questions that will drive future generations of scientists to seek deeper answers. The mysteries of radiation are far from solved, but that is precisely what makes it such a captivating and vital area of study. The ongoing journey to understand radiation in the context of quantum physics offers an opportunity not only to unlock the secrets of the universe, but also to refine our understanding of the very nature of reality itself. Whether we're exploring the invisible forces that govern the behavior of particles, or looking up at the stars and galaxies that illuminate our sky, radiation remains a fundamental part of the cosmic story, a story that is still unfolding. As we continue to explore and probe the quantum world, the ongoing mystery of radiation will undoubtedly continue to shape the future of science, technology, and our understanding of the universe. The questions we ask today will lead to new insights tomorrow, and the pursuit of knowledge will continue to drive us toward new frontiers. In the ever-evolving quest to understand radiation, we are reminded that science is not just about finding answers, it's about exploring the unknown and embracing the mysteries that continue to challenge and inspire us.